Alright, so let's talk about the second derivative test. So why do we need another derivative test? Well, in the first derivative test, what you need to do is you need to look at a function f and you have to differentiate it and figure out when its derivative is positive and negative. This isn't the end of the world, but it takes a fair amount of work to sort of look at a function, differentiate it correctly, and then find all the intervals where it's positive and negative. It's a bit of a long inequality problem to deal with. Because of that, one might want a test that doesn't require so much work. And we have one, and it doesn't always work. This test can fail, and I'll explain that. But nonetheless, the second derivative test says the following. Let C be a critical point of f at x such that f prime prime of c exists. So remember, a critical point, in this case, if the second derivative at c exists, we need to have that the first derivative exists, so of course this is a point where the first derivative f prime of c is equal to 0. So then, what can we say? If f prime prime of c is greater than 0, then c is a local minimum for f at x. If f prime prime of c is less than 0, then c is a local maximum for f at x. And if f prime prime c is equal to 0, the test fails. And what do I mean by the test fails? I mean that we don't know. So first, for the two bullet points in the affirmative, let's draw a quick picture to see why we should think that this is the case. So if we have a function that looks like this, and we have a local minimum here, well then what's happening? If you think about the tangent line, at this minimum the tangent line is 0, but beforehand it's going up, 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 so you can think of the tangent line, its slope is growing, which means that the acceleration of this guy, if you think of this as the path of a particle in space, this guy has positive acceleration. And positive acceleration means that the second derivative is positive. So that's why this condition here will force c to be a local minimum. Similarly, if you had a local maximum, that would look like something that has negative acceleration at that point c. So that's the basic idea. But what do I mean that the test can fail? I mean, if the second derivative is 0 at the point c, then anything can happen. So let's just do some quick examples of failure. So, 3 quick ones here. If we have f at x is equal to x cubed, note that we have that the second derivative at 0 is 0 for this function, but we've looked at this function a lot before. This function doesn't have a maximum or a minimum at 0. Local, global, anything. No maximum or minimum. So this can happen when the second derivative is 0, but so can the following two things. If you have f at x is equal to x to the 4th, we see that you have that the second derivative at 0 is also 0, but this function does have a local minimum at 0, whereas if you have this guy here, fx is equal to minus x to the 4th, well, this guy's derivative at 0 is also 0, but it's a maximum. So this test gives you a trade-off. It's often easier to use this test than it is to use the first derivative test, because you have to do fewer computations and you don't have to do a big inequality problem. So if you can apply this test, that is to say, if the second derivative at c is non-zero, this is generally a faster test to use and gets you an answer faster than the first derivative test would. However, note that if the second derivative at c is 0, you really can't say anything. We say the test fails because apparently there are examples of functions that have critical points where the second derivative is 0, which have maxima at that point where the second derivative is 0, maxima, minima, or neither. So the test necessarily fails if f prime prime of c is equal to 0, and you have to use another test. Okay, let's go through some examples. Okay, now let's go through two examples, one we've seen before and one we haven't. So let's talk about f at x is equal to x cubed minus 9x again. Nice little function. Well, remember, what do we have? We have that its derivative is 3x squared minus 9, which is this. So as we've seen a number of times, we have critical points at root 3 and minus root 3, but now we can show that these points are local maxima and local minima respectively a lot faster than before. Because what is the second derivative? The second derivative of this guy is going to be 6x, and we note that f prime prime of minus root 3 is going to be minus 6 root 3, which is less than 0. So this guy has got to be a maximum, because indeed this point has negative acceleration here, so the curve is going up and then back down again. Whereas f prime prime at root 3 is going to be 6 root 3, which is greater than 0, which means that this point has to be a minimum. And this is exactly what we've seen in the past, with this point here being minus root 3 and this point here being root 3. But I think we can agree, and if you compare to sort of our discussion of this function before, this is a pretty quick way. We didn't have to do a lot of work to see that this point was a local maximum and this point was a local minimum. So hopefully this sort of illustrates, in comparison to earlier examples, why we kind of like the second derivative test, at least when we can apply it. Though again, be cautioned that you can't always apply it, as we talked about before. Now, another quick example. Let's just do another polynomial one, because why not? It's something we can really sink our teeth into. Let's just talk about x to the 5th minus 80x plus 7. That's a pretty high power of x, but I made sure that everything factors properly. You'll definitely see examples like this as you go forward. So let's talk about how this works. Well, what is the first derivative? Well, we have that the first derivative is 5x to the 4th minus 80. But just with a little bit of factoring, we can see that this is 5 times x to the 4th minus 16. But this is a difference of squares. This gives us 5x squared minus 4, x squared plus 4, which gives us 5 times x minus 2, x plus 2, x squared plus 4. So we have critical points at 2 and minus 2, just with a little bit of factoring. Okay, so obviously this function, it's a degree 5 polynomial. It's a little nasty to graph. You can graph it afterwards if you want on a computer, but if something like this showed up on a written test, this isn't the type of thing you really graph. So it's hard to say exactly what the shape of it is. But still, even though this is one that's a little beyond our grasp to easily graph, we can still use the second derivative test to determine if these points are local maxima or local minima. Hopefully the test doesn't fail, but hey, let's give it a try. We have that the second derivative of x is going to be 20x cubed. So we have that g prime prime of 2 is going to be 20 times 8, and that's going to be greater than 0. So it would seem that the point 2 is going to have to be a local minimum. And similarly, we have that the second derivative at minus 2 is going to be 20 times minus 2 cubed, which is going to therefore be less than 0. So we have that at -2, we have a maximum. So this is fairly exciting. This is a graph that we knew how to draw, so we sort of expected, what was coming, because we'd seen this graph before, and this just confirmed it for us. But we're not, without a computer, quite too sure exactly how this looks. But nonetheless, without doing anything else, we're able to at least find where its local extrema are, and we're able to classify them as minima and maxima, respectively. So that's the power of the second derivative test.